So this is example number 3 for thin airfoil theory. In this example, it's more of a design example. So let's suppose I have a camber line that's given by the following equation. And what you're asked is, find what are the values of A and B. So I want to find the values of A and B. I don't know what these values are. And I want these values such that the moment of the airfoil at 0 lift is equal to 0. Okay? So those are the two conditions I have. So before I start my problem, what I want to do is I have to define a few things. So first I need to know what limits I'm working with. It typically is commonly very beneficial to divide your domain by your chord length and go from 0 to 1. And your theta, then you go from 0 to pi, okay? With this given, then you know that x over c will be 1/2 1 minus cosine of theta, and we did that in class already. So number 2, two quantities that I'm going to need, so might as well go ahead and let's go ahead and find it. I take the derivative with respect to x. That gives me 1 minus 2a x over c plus 3b x over c squared. Okay, and then back to t. So I replace now, use this replacement everywhere I have these expressions. After I do that replacement, I find that this is equal to 1 minus a plus 3/4 b plus a minus 3/4 b cosine of theta plus 3b over 4 cosine squared. Okay, so that's what the expression gives you. So I know I'm going to need my coefficients, so might as well go ahead and calculate what these coefficients are. A sub 0 is equal to minus alpha plus 1 over pi 0 to pi partial of eta c of x theta d theta. This is minus pi, and this will give you, replacing the whole expression in there, you get the following. So just know that all I did was I replaced here, here I replaced what I got here. Okay, so this expression, I got one expression, two expressions, three expressions. That's where we have one integral, two integral, and three integrals. And after you integrate each one of these, you can just show that the answer that you're going to get for a sub 0 is equal to this. Okay? I let you do all the mathematics behind that. Similarly, a1 then is going to equal to 2 over pi, 0 to pi, partial of c respect to x. The theta is 1, so cosine, this was n, instead of n you put 1, and you replace, and this is what you get. Okay, again I got three expressions, because I have three terms that are going to go inside here. And after you do the integration and you simplify, this is what you're left with. Okay? Now I do the same thing for A2. Zero to pi, partial of eta, partial of x respect to theta. Now note that cosine is 2 theta. Okay, so now it's 2 because this is 2. And if you replace everything, this is what you get. Okay, so when you replace, you got one term, two terms, three terms. That's what we replaced there. And this is what you end up with A1, A2, A3. Okay, so we know, and you can show this to yourself, okay, that the condition for 0 left at 0 left, what we have is typically x is equal to c over 4. Then your moment requirement would be Cm, replace wherever we have x for 4, you have a sub 0 pi 1/2 minus 2 c over 4 1 over c plus a1 pi c over 4 1 over c minus 1/2 plus a2 pi over 4. Simplify the whole thing. You find that this is equal to pi 4th a2 minus a1. Okay. So from here, the condition for this to be exactly equal to 0 leads you to the fact that this will be pi over 4k a minus 15 over 8b. This is replacing the value of a2 and a1 here. So you find from this is 0. So you find that a is equal to 15 over 8b. This is one expression. This is, and then the second expression that we know, we have to apply the CUDA condition. That's important. Okay. At trailing edge, so at the trailing edge requirement, we know that at x equal to c, at the trailing edge point location, that has to be 0. So if I take this expression, your c that was already given in the problem, and I replace it with, I replace x with c plus b c over c squared is equal to 0. This gives you 1 minus a plus b is equal to 0. You got a system of equations. Now you solve your system of equations. You have the first system, a minus 15(8)b is equal to 0. Minus a plus b is equal to minus 1. You can solve that. A is equal to 15 over 7. B is equal to 8 over 7. So therefore, your final answer here would be eta of x would be minus k of x. 1 minus 15 over 8 x over c plus 8 over 7 x over c squared. This has to be your Camber equation. For this is how we do a design problem to make sure this happens. Just want to point out a few things here. Remember, this is really a cubic equation because this x has to be multiplied. That's the only reason that when I took the derivative, you have a 2 there and you have a 3 there, okay, because this is a cubic equation. Okay, so this concludes example number 3.